So the first thing that I want everyone to do right now is to open Ghidra properly. So like wherever you have Ghidra installed, right, or downloaded to, I want you guys to open it. So last week you should have already made a Ghidra project. So I'm just gonna open my copy of Ghidra here.
Please open Ghidra.
And you should see the projects window like this. I want everyone to have their project window reopened, right? Okay, so we're going to be looking at ELF number 2. So everyone go over to day 2 materials, then go to decompilation and ELF 2. So inside this folder, you should see 3 files. You should see second, batch decode, and decode.py, right? And inside this folder, I want you guys to open a Linux window. Open a Linux shell. Yeah, so run the second ELF file, right? And then just play around with it and see for yourself what the program does, right? I want everyone to familiarize themselves with what they expect to see inside the program when they do some reverse engineering later. So everyone should be able to run the program and interact with it. And we should see some things that we expect to see inside the ELF file. So can someone tell me, if I do strings on this, what do I expect to see? Like what does strings give me when I run it? Usually when you run strings on a program, what you expect to see is the readable text from the program. So in this case, we know that this program is supposed to have the text Singaporean DeepSeek, it's supposed to have the text calculating, supposed to have the text bye-bye somewhere, right? But if you run strings, you don't see any of it. It's missing. I mean, you see some text that might be relevant. You see prompt, right? You see something that looks like what we're expecting, but isn't actually the text, right? And you see some of the other like common text that comes with ELF files, your section names, your function names, right? But we don't actually see the strings that we expect to see. So anyone want to guess why this is the case? Why do we see this instead of the strings that we're expecting? Ciphered it, right? And what? Well, that is a form of data obfuscation, right? So we're going to look at that inside Ghidra, actually. So first thing that we're going to be doing, right, importing the file. So if you guys have forgotten how to do this, we're just going to do it here. Instead of pressing I, you can also just drag and drop the file into Ghidra. So you take this, drag and drop it here, and then you just press OK. Like for all the prompts that come up, right, you just go OK. This one also go OK. Then once everything is fine, right, you press the small dragon while the file is highlighted, and then it will launch it. So while here, okay, the program itself isn't open. So Control O, or like open, file open, and then second. So there's two ways to do it. It's either you do small dragon and then open, or from the original window you just double click on second and then it should bring you to this. Is everyone waiting on this prompt now? It should ask you to analyze, right? Okay. Yeah. So for people that have already made it to this stage, right? When they ask whether you want to analyze, just press yes, and then on this big window, don't touch anything. Just press analyze. It will automatically do the analysis for you. So everyone should be able to see this. For now, it should say no function here. So right now, you should see no function on this side, but you should see main on this side. When you click on the pink color main text, right, it will then show you the decompilation of main. So if you just click the pink color main on the left side, then you will see the pseudo code output from Ghidra on the right side. So this is the decompilation or the approximate source code that Ghidra has recovered from the program. Okay, so first thing that I want you guys to think about, right? do you notice that there's anything interesting about the functions here? They have names. Yes, exactly. So the thing is, usually in a decompilation output, your functions do not have names all the time, right? Because that is a piece of metadata that the compiler doesn't need to retain. Your output program doesn't actually need to know what a function name is. It just needs to know where the function is, right? However, in this case, we do have the names of our functions here. So if we reopen our Linux window, right, I want you guys to type file and then second. So the file command will give us some information about what the file is, right? It'll use the magic and pull some of the metadata. But the really important point here is the last line, not stripped. So when a binary is stripped, that means its metadata has been removed, which means the function names will not show. But because this program is not stripped, so the function names are still there. And the function names makes the program a bit easier to approach at first glance, right? Because what did we see just now when we ran the program? We saw it ask for a prompt, right? Singaporean DeepSeek asking for a prompt. Then it did its computation, and then it did some like the progress bar, and then it did a computation at the end, right? So this corresponds directly with what we saw inside the program. Okay, so another thing that I want you guys to try. So in the top left corner, right, on the program tree, there's this really small button, right, which is a green arrow pointing at a rectangle. I want you to click it. So when that happens, right, you shouldn't see much change, except now you should see one of these lines is being highlighted. What this does is when you are in a specific section, right, it will tell you what section you are in. So what section are we in currently? Text, the .text section. Why are we in the .text section? Yeah, what's in the .text section? Code, the machine code for the program. And when we're looking at the functions, we are looking at the machine code. So we expect it to be in .text. If we go to different sections, right, we will see different things. So for example, but if we go over to like some other part of the binary, you can see it now changes what section it says we're in. So just scroll and click. You can see we're jumping around here, right? But when we're in the code section, we are always in .text. Okay, so the first thing that I want you guys to step through is the decompilation for the prompt function. So to step into a different function, you just double click on it inside your decompilation view. So if you double click on prompt, you should now see the decompilation output for this function. So for people who have only used Python, a lot of this syntax might seem unfamiliar, but like believe me, right, the syntax is simple enough for these decompilation outputs to understand what the programs are doing. So first thing that I want you guys to notice, right, there is a MEMCPY function here. Can someone tell me what MEMCPY is? You can Google this. You can Google this. Memory copy, right? What does memory copy do? Copy memory from like how? From one place to another, correct. So memcopy copies memory from one place to another. The function signature, or like the parameters of this function, is this is your destination, this is your source, and this is how many bytes you want to copy from the source to the destination, right? Does anyone remember how to change it from hex to decimal inside Ghidra? Because right now it tells us it's copying 0x1e bytes, but we like looking at decimal numbers instead. Does anyone remember how to change it? Yeah, so when you right click on a hex number, you can see all the different equivalent data representations you can change it to. So for example, 0x1e, we can change it to the number 30, right? Because that's what it's equal to. 0x1e is equal to 30. So if hex is unfamiliar to you, you can change to decimal to make it easier to read. Okay, another thing that I want you guys to notice. So just now we double click at prompt, into prompt, and then it showed us this, right? I want you guys to double click on mem copy. And I want you to notice that there is no decompilation output. So the interesting thing about this is memcopy is not a function that's implemented inside our program. It is an external function that we import into the program. So it's the same concept as Python imports. You know, when you do import math, then you do like math dot sign some number, right? When you use the math library in Python, you don't copy paste the source code of the math library into your script. You just tell Python I'm importing math and I'm using a math function. Similarly, inside an L file, you can tell the system, hey, I'm not implementing memcopy. I'm going to import memcopy from a different library and I want to use it, right? So this logic still applies. And in Ghidra, you can see all the imported functions over here. So in the program tree, I want everyone to do this. In the program tree, under imports, you can open this up and you can open external. And then it will show you every function that we're using that isn't implemented inside the program, but it's an external import into the program from a different library. So these are all external functions that we are importing from outside of the binary that we're not implementing inside the binary, right? That's why the decompilation output doesn't show. And we are using it in our own program for our own means, right? So as mentioned just now, memcopy is one of these external functions, right? So even though it is being imported and we don't have it implemented here, if I go all the way back to, okay, to return back to the functions we are analyzing, right? There's the functions folder on the left here. We're going to go back to main. Where's main? I can't see. I'm going to go back to main. I'm going to go back to prompt, right? So even though memcopy is not being implemented here, when you double click on memcopy, it still shows us what is called the function signature. So a function signature tells you what inputs the function is expecting. So just now, I asked, when you do memory copy, right, where do we know what you're copying from? So in this case, it tells us the destination is the first argument, the source is the second argument, and the size is the third argument. So it helps us to read what we're doing here. This is the destination, this is the source, this is the size. This is the destination, this is the source, this is the size, right? This is information that we can still get even without the decompilation output. So one more thing that we're going to look at, right? Inside this function, there's the decode function, right? And the moment you look at it, you'll notice that it's a bit longer than what we've been looking at so far. So we will break down how this function works, right? And then we will use this to map back to our understanding of the program. So before we continue with our analysis, we need to talk a little bit about variables, right? So when we're working with decompiler output, right, renaming variables is our first step in getting a clearer understanding of what the program is doing. Because right now, we just have generic names, local 98, local 58, right, local C. When you are writing code, you're not naming your variables local 98, local 58, local C. You're naming them things like destination, destination buffer, array, um, I, J, K, you know, for for loops, right? You're not going to be using generic names like this. So we want to rename variables to make them a bit easier to read. So for example, what we're going to do inside the prompt function first. Everyone go to the prompt function. Go back to the prompt function. You notice there's a for loop here, right? Now, for loop, usually you would just use a short character name for your index, your loop index. So for example, local C, you click on it to highlight it, should be in yellow. Then you press L. When you press L, the prompt to rename should come up. Then you can rename it to something. So usually when you do for loops, it's like for I in range, for j in range, something like that. So we just name it I. And then now the for loop looks a bit cleaner, right? This looks a lot more like how normal code would be written. And then let's try filling in some other variable names, right? So just now we said memcopy takes a destination, a source, and a size, right? So what should I rename local 98 to? destination. I mean, we have, okay, so we have two mem copies. So maybe we call this destination 1. And then we have another mem copy. So maybe we should call the next one destination 2. This should make the code a tiny bit more readable. Yeah, so if y'all are in the wrong function, please go over to the left side, right? Function in the program tree. You open up the function folder, and then you should be able to find the function here. Like let's say you want to go back to main, right? When you're here, you go and look for main. You double click and it will bring you back to main. Just now we were looking at prompt, so you go to prompt and then it will show you prompt. All clear? Can you do the renaming now? We rename the local variables. So you select the thing, you press L, then you can rename it. Can. Okay. So everyone's decom output should now look a bit cleaner, should look a bit like this, rather than seeing local, local, local here and there, right? This is something that I cannot do to demonstrate because I don't have a mouse. But if you want to see every time a variable is being used inside a function, you can middle click. You can middle click the variable and it should highlight all instances of it. So assuming that you are able to do that, I can't do it because I don't have a mouse. We are going to continue on, right? Another thing that, okay, so this is something that we saw earlier, right? We're gonna go into the decode function now. Inside the decode function, can someone suggest what we should rename local C to? For J in range, okay. And then we can see that svar1, right? Svar1 is the output of strlen. What do we determine strlen to do just now? String length, right? So what should we name svar1? Length, len. And what do we pass into the string length function? Your string, right? So this is input string. So is everyone able to get something that looks like this? Can I get a thumbs up if you manage to make it here? Okay, yeah. So assuming that you managed to get to this stage, right? So something that I want you guys to notice as well. Do you guys remember the ASCII table? Yeah. So if you look inside this loop, you can see 0x41, 0x5a. I'm just going to throw a bit of a spoiler here. These are meant to be characters. So what we can do, just now we were changing from hex to decimal. You can also change from hex to character. So 0x41 is the character big A, and that's big A. And does anyone know the character for 0x5a? Yeah, that's big Z, right? So you see, even now, just by doing a bit of cleanup in our decompilation, we can already sense a bit of the logic of our decode function. It's iterating through our input string, character by character. We know it's character by character because we're in a for loop, right? And then we check if the input string is smaller than A, which means the character is the numerical value in ASCII is less than A, or greater than Z. So that means it's outside of the range of the big alphabet. We can do the same thing for the next if statement. So 0x6a, that is the backtick character, and 7b is curly brace. So this just binds you to another range, right? So now it checks whether input string is greater than 0x6. What is it again? 60, right? If I pull up Python, so can we agree that it's equivalent logic that being greater than 0x6a is the same as being greater than or equal to 0x61? Can we agree this is equivalent logic? So if we check what 0x61 is, not odd, CHR, sorry. 0x61 is small letter a, right? Similarly, at the end of the range is 0x7b, right? So can we agree it's equivalent logic that less than 0x7b is equal to less than or equal to 0x7c? Not 7c, 7a, 7a. 7a in the ASCII table is the small letter z. So we see now we have two bounds checks, right? We're checking whether something is outside of the big alphabet range or if something is inside the small alphabet range. This makes sense to everyone so far? Another thing that I want to touch on here, so now that we've done some renaming and our renaming has let us understand a tiny bit of what this function is doing now, right? So now we know that it's taking a string length, it's iterating through the string, it's checking whether our string characters are within the alphabet range, right? Let's talk a bit about globals. I'm going to jump a bit here and let's talk about globals. So global variables versus local variables, right? I hope you guys are familiar with this from something like Python. So global variables are variables defined outside of functions and are accessible to every function inside the program, right? In the case of a compiled program, a global variable is often initialized before runtime, which means if it has a value, that value is baked into the binary, right? Local variables are limited to the scope of a function. So that's why just now when you were looking at the function, it was called local whatever, right? Those are variables inside the function, not accessible outside the function. So in Ghidra, when you see a variable that is colored blue, that means it's a global variable. So for example, inside this decode function, which of the variables is global? Someone just say it out. Unless you're colorblind, in which case I'm sympathetic. Mod. So mod is a global variable. And you can notice if you double click on mod, it will send you to a different section over here. So again, like just now we were in .text, right? When you double click on mod, what section does it say we're in the program tree? On the top left? Data. We're now in the data section. And inside the data section, this is where the value of mod is being stored. So the value of mod is 0x1a, right? And 0x1a is equal to, can someone do some quick math? Is equal to 26. So we know the value of mod is 26, right? And it's a global variable. If we go back to our prompt function, so I'm gonna look for prompt and I'm gonna go back there. What are the global variables here? You should see 3. Yeah, S0, S1, and standard in are global variables here. So again, if you double click on S0, it will bring you in the disassembly view to where the variable S0 is being defined. In this case, this is the value of S0, which is some ciphered string, right? If I double click on S1, it will bring me over there and it will show me the value of S1 and it's some ciphered string over here, right? If you double click on standard in, you're not going to see something that you really understand, right? It's just zeroed out here. This is not relevant to what we're going to be covering. But just remember, S0 and S1 are global variables. And if you remember, memcopy copies memory. So we're taking this value that S0 holds, whatever this is, and we're going to copy it into destination 1. Or we're going to take whatever value is here, that S1 is, and we're going to copy it into destination 2. Is everyone clear on this? Okay, so back into our decode function. Okay, these are just slides showing what I was just showing y'all. Alright. So what type of obfuscation is being used here? Just now we basically got our answer lah, right? But I want someone else in the audience to reply. So when we look at S0, we see a string that looks like this. What sort of obfuscation is this? Just use one of the generic names. They're both under the umbrella of data obfuscation, right? Because at the end of the day, like I said, usually you should be able to strings out something like this. You should be able to run strings on the binary and see what this is supposed to be. But in this case, we can't. So that means that the data inside the program has been obfuscated somehow. So what we can do is we can re-implement the function that we have inside our decompilation output into something we're more familiar with. So in this case, it's in C right now, right? So this is decode.py. I want you guys to notice that the functionality inside Ghidra of this function, we have copied it over and rewritten it in Python for you guys, right? And you should be able to see similarities in the structure. For example, this for loop, which goes up to the length of the string, is mimicked here in this for loop, which goes up to the length of the string, right? The first check, where we check whether it is within the bounds of the alphabet, the big alphabet, is replicated here, checking whether it's within the bounds of the big alphabet. This check here, which was if we're within the bounds of the small alphabet, is re-implemented here, same thing. And then for each of those branches, we copied over the logic that we have. So this is some assignment, right? Some long expression. We've copied that expression over here. And then this value, this is our original modulus, right? Just now we saw mod, global variable, with the value 0x1a. If we wanted to really copy the code one-to-one, right, what we could have done is we could have made a global variable mod equals 0x1a, and then we could have put it here. Then this is really replicating what we see in Ghidra. Everyone clear on this? Right? This is re-implementation of logic, right? And when we re-implement functions in a programming language that we're more familiar with, it might be easier for us to analyze it, right? Because like let's say you get an output from Ghidra, you don't want to have to compile a C program with similar C code every single time you want to test the function to see what the function is doing. A lot of testing in reverse engineering is semi-black box-ish, right? So in the sense that when we look at this function, we may not immediately know what it does. However, by putting in some inputs and putting out and getting some outputs from it, we can sort of see how the function is behaving. And based on how the function is behaving, we can figure out what the function is doing. So what I want you guys to try is inside the folder, right? Because everyone should have decode.py inside this folder. So open your terminal and then run decode.py. Oh, whoops. Python 3, forgot for WSL. And then you can just put in some input string, any input string of your own. Hello, bro. And then you should see the output of this function. So when you're playing around with something like this, for example, if I put in all t's, right? Notice that all the t's get turned into g's. And if I have another string, the t in that string also gets turned into a g, yes? So again, if you run python decode.py, notice that it's very consistent for the inputs that you're passing in, right? It doesn't change if you run it separate times. And it seems to be doing some sort of mapping of our characters into other characters, right? However, if I put in numbers, nothing happens, right? Or if I mix it up with numbers, the numbers don't get touched, but the characters do. If I put in some other string, right? If it's small letter characters, it also gets transformed. If it's big letter characters, it also gets transformed. So we know that it's doing something between big characters, like big alphabets, and small alphabets, right? And transforming them into something else. Has everyone played around with this? Is everyone clear on what this has re-implemented? Okay. So what this one actually is ROT13, right? This is a ROT13 encoding, right? So this is something that we can see in CyberChef as well. So how would you have reasoned that this is ROT13? Well, two ways, either by observation or by reading the code. So for example, this code is a bit hard to read, but it's because it's doing something a bit tricky here, right? If I want to perform ROT13 on a string, so if my original character was A, when I do ROT13, I would go to 13 positions later, so my A turns into N, right? Or if I started with B, my B would turn into O, right? It's a shift. It's a shift of all your characters. See, A goes to N, B goes to O, C goes to P, D goes to Q, so on and so forth. This is ROT13. And this is what's actually being implemented in the code. I guess I'll just leave this as an exercise to you all to figure out, because it might be a bit hard to understand here. But by equivalent logic, right, minus 0x34 is equal to 0x41 plus 13. You guys can think about that, I guess. I think that's true. 0x41 minus 13. Yeah. So these these are equivalent expressions. Maybe you guys can think a little bit about what the implication here is. Because remember, rod 13 is shifting the character by 13 places, right? So what we're doing here is we are shifting it by 13 places, but we are minusing a small constant first. Okay, I'm not gonna stick on this point because I wanna really continue with this part. So now we know it's rod 13. And the thing is, rod 13 is a known algorithm. So this is not something new that the malware author has come up with, right? Some of the people here already knew what rod 13 was. So if we were to take some of these output strings, so let me just create an output string. This is an output string, right? And then if I take this string, and then I go into a website like CyberChef. So if I go to CyberChef and I paste it in, I can use rod 13 and it will perform the same functionality that was implemented in both the L file we were looking at and in the Python script that we were looking at. Everyone clear on this? So now that we have a way of performing rod 13, and mind you, the inverse of rod 13 is just rod 13. Anyone want to explain to me why? Yes, and what is 26 equal to? 26 is equal to 13. Close. 13 plus 13, correct. So if you shift by 13 to rotate 13, then you shift by 13 again, you do one full rotation, like the world, right? So you go back 26 places and you're back at where you started. If we want to recover the data, so now inside the program, right, all of our globals, like our global strings, so if we go back to from, we had S0 and S1, right? And those, now we know that S0 and S1 are rod 13 encoded strings. Agree? So how do we extract out the strings so that we can unrod 13 them ourselves, right? So inside Ghidra, right, there are different ways that you can export stuff. So I want everyone to do this. From go back to S0, right? Go back to S0. Then you should see it over here in the disassembly view. Then I want you to highlight this entire thing. So the whole thing must become green. Then afterwards, when you right click, there should be an option called copy special. Copy special, you can then copy, you scroll down, you should see Python byte string. So this is a really, really useful feature in Ghidra. After performing copy special with the byte string, like Python byte string, when you control V, this is a Python compatible byte string. So I can just paste this into Python and it's valid syntax, right? What we can do now that we have it in byte string form, right? I want you to go to batch_decode.py, right? In batch_decode.py, I want you to replace the first encrypted string with the byte string that we just copied. So you replace question mark with the first string that we just copied, which should fill in like this. So I want everyone to do this, but for the second string as well. So S1, you guys copy it yourselves, right? Go S1, highlight the thing, copy special, and then paste it in. Oh, see, I messed it up also. Highlight the thing, copy special, and then paste it in. So once you paste it in, right, your script should look something like this. You should see 2 byte strings, 5B, 21F, 5D, so on and so forth, then 435952, so on and so forth, right? These are S1, sorry, S0, S0 global from the binary. So it's S0 and it's S1. Okay, so if everyone has managed to paste these in, you should be able to run batch_decode.py and you should see the output and you should see something familiar from the original program. So our first string, right, which was encoded like this, after we perform rod 13 to decode it, we get back Singaporean DeepSeek, which is the name of the which was what was printed. And then we had this encoded string, we decode it, and then we get please enter your prompt here. Everyone managed to get these outputs? So yeah, what we have managed to do here is we managed to take what is obfuscated data inside our program and deobfuscate it, right? So yeah, this is what you guys should have seen at the very end. And that's all for ELF2. So what did we learn from looking at this binary? We learned about symbols, right? What were symbols again? The name of the function, yeah, the fact that the functions had names, right? The fact that they were called prompt and decode and calculate and so on and so forth. Those are symbols. Then we looked at imported functions. What were some of the functions that were imported into the binary? You can just read off, Gedra. Memcopy. Any other answers? Printf. Fgets. Okay. Then next, we did some dynamic deobfuscation. So what we were doing was we were running the equivalent version of the function but inside Python. And by running it a few times, we could make some observations about how the inputs affect the outputs. And then we could reason about that this was rot 13. Then once we knew it was rot 13, then we could think, oh, how does rot 13 work? It shifts our characters by 13 characters, right? By 13 slots. So how do we invert the function? We shift it by another 13 slots, right? And then we could deobfuscate the strings ourselves once we established it was rot 13. So that's ELF2, right? I'm gonna take a 5-minute break before we do ELF3.